Good morning, class. All right, Unit 2 is over. Today we're going to start Unit 3. And our topic today is exponential functions. Day 1. Okay, so let's get a definition to start with. The exponential function f with a base of b is defined by f of x is equal b to the x, or y is equal b to the x. So example, f of x is equal 2 to the x would be an exponential function. G of x is equal 10 to the x is also an exponential function. H of x is equal 3 to the x plus 1, and j of x is equal 1/2 to the x minus 1. So all of those are exponential functions. Now what we notice with an exponential function is that each of these has a constant for a base and a variable exponent. So each has a constant base and a variable exponent. So by that definition, is f of x equal pi to the x an exponential function? Okay. So pi is an irrational real number, but it is a constant. And we still have a variable base. So the answer there is yes. That is still an exponential function. Now, f of x equals x squared. This is an algebraic function. Your base is a variable, and your exponent is a constant. So this is algebraic, not exponential. What about 1 to the x? Or negative 1 to the x? Is this exponential? Well, no. 1 raised to any power is 1. So 1 to the 30th power is still just 1. So keep in mind you have 30 factors of 1. So your answer is 1. So 1 to the x is a constant function. And similarly, we could show that negative 1 to the x is also a constant function. So no, those are not exponential function. Okay. So we're going to start off just making sure that we can use the calculator correctly. So make sure you have a calculator, either one of mine or one of your scientific calculators, because we're going to graph some of these functions, and we want to make sure that we're able to evaluate an exponential for any value. Okay. All right, so we'll pause and let you guys grab a calculator if you don't already have one. Okay, so let's say we have f of x is equal to 23.4 times 1.08 to the x. Okay. So this is an exponential function. Your base or b is 1.08. Our variable is an exponent. But we're also going to multiply this by a constant. So just remember with PEMDAS, your exponents come before multiplication. So this part is processed, and then we multiply by the 23.4. So let's say we wanted to evaluate f of 3.25. Then that'll be 23.4 times 1.08 to the 3.25 power. So what does that look like on the calculator? All right. So here's our calculator. Okay, so let's go ahead and turn it on. All right. So you can actually enter it on this calculator just how it is. So we can go 23.4 parentheses 1.08 close our parentheses, and your exponent button is right below the x squared here. So it's this button here, exponent, and then we're going to raise that to the 3.25, and enter. So that value is 30.0499. So the exponent button again is right there below the x squared button. Okay. So let's take a look at what an exponential function looks like graphed. And we'll start with graphing an exponential function. So we'll start with f of x is equal to the x. Okay. So let's generate a table of values. So we'll start with x, and then f of x is equal to the x. And we'll use values of -3, -2, -1, 0, 1, 2, and 3. All right, so f of -3 is going to be 2 to the -3rd power, which is 1 over 2 to the +3rd power, which is 1 over 8. F of -2 is 2 to the -2nd power, which is 1 over 2 squared, which is 1 over 4. F of -1, 2 to the -1st power, which is 1 over 2, or 1/2. f of 0 is 2 to the 0, which is 1. f of 1 is 2 to the first power, which is 2. f of 2, 2 to the second power, so that one's 4. And then f of 3 is 2 to the third power, and there we have 8. So our graph so when x is equal to -3, we're at 1/8. So we're getting close to the x-axis, but not quite there. When x is -2, we're at 1/4. When x is -1, we're at 1/2. When x is at 0, we're at 1. When x is 1, we're at 2 to the first, so that's 2. When x is 2, we're going to go up to 4. When x is 3, we're all the way up here at 8. So our graph looks like this. When x is 4, 2 to the 4th is 16. When x is 5, 2 to the 5th is 32. So it's really climbing fast. So your domain, or our domain, all real numbers. Our range are all values of y such that y is greater than 0. So this function will never be negative because 2 to the -100th will be 1/2 to the 100th. So that's still a positive value, but it's getting closer and closer to 0. So you do have a horizontal asymptote of y equals 0 or the x-axis. There's no vertical asymptote. And as x goes to -infinity, f of x goes to 0. So the limit as x goes to -infinity is equal to 0 of f of x. As x goes to positive infinity, f of x goes to infinity. So as x increases without bound to the right, our y values increase without bound. Okay, so let's take a look at another graph. Okay, so that was f of x is equal to 2 to the x. Let's take a look at another graph. This one, let's say f of x is equal 1/2 to the x power. So we're going to still create our table of values. So f of x is 1/2 to the x. Okay, we'll still go with the -3, -2, -1, 0, 1, 2, and 3. So here, when x is equal to -3, then f of x is going, f of -3 is going to be 1/2 to the -3rd power. So 1/2 to the -3rd power is the same thing as 2/1 to the positive 3rd power, or 2 to the 3rd, and you have 8. 1/2 to the -2nd power is the same thing as reciprocal 2/1, or 2 to the positive 2nd. So we get 4. 1/2 to the -1st power is the same thing as 2/1 to the positive 1st power, so that's 2. 1/2 to the 0 power is just 1. 1/2 to the 1st power is 1/2. 1/2 to the 2nd power is 1/2, 1/2, 1/2, 1/2 times 1/2, or 1/4. And 1/2 to the 3rd power is 1/8. So graphing here, Let's take a look at our graph here. Okay. All right, so when x equals -3, we're all the way up here at 8. When x is equal to -2, we're at 4. When x is equal to -1, we're at 2. And then when x is equal to 0, we're at 1. When x is 1, we're at 1/2. When x is 2, we're at 1/4. When x is 3, we're at 1/8. So our graph is going to take this pattern. Okay. So in this instance, our domain is still all row numbers. Our range, all values of y such that y greater than 0. And as x goes to -infinity, f of x goes to infinity. As x goes to positive infinity, f of x goes to 0. So we do have this horizontal asymptote of y is equal to 0. All right, so now we're going to take a look at these exponential functions and graphing them with all of the transformations that we've learned before in Algebra 2 and at the beginning part of this class. Okay, so we will start with vertical translation. So f of x is equal b to the c, b to the x, plus c, and f of x is equal b to the x minus c. So this shifts up. C units. And f of x is equal b to the x minus c shifts down. C units. So that's our vertical translation. Horizontal. So just like before, so in this case, f of x would be b to the x plus c. So this would shift c units. What do you think? To the left or to the right? So think of our horizontal translation. So this would shift c units left. And f of x is b to the x minus c, would shift c units to the right. Okay. Our reflection. Okay. So this one you have 2 f of x is equal negative b to the x, and f of x is equal to b to the negative x. So do you remember which one of these is a reflection over the x-axis and which one is a reflection over the y-axis? Okay, so the first one reflects over the x-axis. So -1 times b to the x is a reflection over the x-axis. b to the -1 times x is a reflection over the y-axis. Okay. And our vertical stretch So that one is f of x is equal c times b to the x. Now, if c is greater than 0, if c is greater than 1, then you have a stretch. But if c is in between 0 and 1, so c is greater than 0 and less than 1, you have a shrink. That's a vertical shrink. So just think about all of your y values just coming down. Vertical shrink. Okay. And our horizontal stretch and shrink. So with that one, that's f of x is equal b to the c times x. So here this is horizontal, so you will have a shrink. Can't spell shrink. So this is kind of counterintuitive to the vertical. So you have a shrink for if c is greater than 1, and a stretch for c between 0 and 1. Okay. So remember, we say between 0 and 1 because if c is negative, that will not only be a shrink or a stretch, but it's going to be a reflection over the y-axis. Okay. So that's why we identify our c as being between 0 and 1 and greater than 1. Okay, so let's take a look at a graph. Let's say that g of x is 2 to the x minus 3. All right. So here our parent function is 2 to the x. And some key values in 2 to the x. Basically, we know that when x is equal 0, for 2 to the x, let's say f of x is 2 to the x. So when x is equal 0, you're going to get 2 to the 0, so we'll be right here at 1. When x is 1, you're going to get 2 squared. We're going to be here. When x is negative 1, 2 to the negative first is 1/2. So we're here. So 3 key points there. So we know our graph is going to do this. All right, so that's our parent function, 2 to the x. So 2 to the x minus 3 is basically you're going to take this function and everything gets moved down 3 units. So when we say everything, we're talking about our asymptotes as well. So all of these points. So here we have a horizontal asymptote of y equals 0, or the x-axis, but we're shifting everything down 3 units. So our new asymptote will be down here. 0 minus 3 is negative 3. This point here at 0, 1, we move it down 3 units. 1, 2, 3. So 1 minus 3 is negative 2. This point here at 1, 2, 2 minus 3, 1, 2, 3. We'll bring it here at 1, negative 1. And this point here at negative 1, 1/2, 1/2 minus 3 will take us down to negative 2.5. So that point will be right there. And then your graph will follow the same pattern as the one before. So here, our domain is still all real numbers. Our range, instead of going from 0 to infinity, now your range goes from negative 3 to infinity. Horizontal asymptote, y equals negative 3. As x goes to negative infinity, f of x goes to negative 3. And as x goes to positive infinity, your function is still rising here. F of x goes to infinity. Okay? So I have a printout for the homework that I'd like for you guys to do. So that homework is